Hello, everyone. My name is Gal, and I am product manager in the networking group. And the session today is about user plan function and acceleration with DPDK. And the background of this talk is that following our implementation of RTE flow with accelerations and implementations of OVS accelerations with kernel and OVS DPDK, we were looking for ways to accelerate additional use cases. And we're looking for different use cases in the networking world, some of which appears to be in the VNF world. And we were looking for the best VNFs to go with. We discussed it with several customers and partners of us, and started to help with different kinds of RTE flow offloading. We discussed it with different kinds of VNFs, and then we ended up with UPF use cases. We have done some experiments with customers, and at some points we engaged with Mavenir, a UPF vendor, and due to the fact that there were no other use cases of open source applications that we can use, such as OVS, it was a very good fit for us to use for testing the use case. And what I will show today is a kind of a summary of what we have learned in the way. We will discuss what the UPF is, what are the challenges of it in the network, and how we think that DPDK can be used for acceleration. To line it up with the earlier discussions, my colleague Elena shows accelerations of the run on the left side, and I will discuss the UPF. Packets, customers, user packets are going from the run, from the mobile, through the run, and then to the UPF. So Elena shows how we can accelerate it on the run. The UPF itself delivers the packets, the customer's packets, the user packets, to the network and the internet. And due to the fact that Elena did a very good job and accelerated the traffic on the run, we don't want to be the weakest link in the chain. So we are trying to do the same thing with the UPF. So a little bit about motivation. I think that we already established a sense of why acceleration is required in the earlier sessions, but just let's do a small recap. So from a data point of view, data demand point of view, world population is still growing. There is a lot of adoptions of mobile phones already, but this will continue to grow through the advanced use cases coming from IoT. IoT devices already populated, but the expectation is by the end of the decade, the number will be doubled. And this will be a very high bandwidth consuming devices, delivering voice, video, used for autonomous cars and autonomous drones and many other use cases in smart homes, smart factories, smart cities. In smart cities, we will be using a lot of video, which consume a lot of data. So all in all, the expectation is that data consumption will be multiplied by 7. Aside to that, or actually align with it, the telco systems are advancing as well. We are now deploying 5G networks in which a single device can deliver more than 1 gigabit, which is more than 10-fold that what can be done in 4G. And the architecture of 5G expects to provide flexibility, performance, scalability, and a lot of other stuff. So this is from the demand side. From the 5G service-based architecture point of view, and there are multiple things that are related to this kind of demand, or actually defined in a way that supposed to align with, based on the technology, should be aligned with being able to provide the capacities that are required. So first thing is that the architecture itself splits the work between the user plane and control plane in a way that most of the network functions are software-based. On the top, we see the control plane. This is an area that we will not touch in the discussion today. And on the bottom, we see the user plane, in which we see the UE, which is the mobile, the RAN, the UPF, and then the data network. So we will discuss all the way that the packet goes through the data network. One item that related to the UPF is the SMF, session management function, that resides on the control plane. This is the kind of the SDN layer that is connected with the UPF and provides the insight about the subscriber, and based on that, the UPF knows how to behave. 2 sessions before, Tobias mentioned the use of DPI. So the UPF uses DPI, and for telco flexibilities, it provides insight about what kind of categories the session is based about. These categories should be aligned with what the SMF presents to the UPF. So if the SMF wants to limit video and allow downloads with even maybe lower quality of service or even lower bandwidth, so this is how it goes. And the SMF provides the insight and the UPF implements it. So the most challenge in UPF and 5G is the transition from hardware-based appliances to software. Telcos are looking for ways to reduce cost and to be flexible. And they are trying to find ways not to put not to rely on specific appliances, but rather to be able to deploy software-based solutions on lower-cost servers. So they are looking for ways to deploy the systems in a way that everything will be containerized. And they're also looking for open standards for similar reason, so that different vendors will be able to provide their solutions. So a single telco will not need to buy all the services from a different vendor from one end. On the other end, all the telco system is combined and communicates one with each other. So it is not possible to be relying on one vendor. So being able to work in standards is very important. We will see at least one standard that is used here, which is a GTP. It is used from 3G and then extended in 4G and further extended in 5G. Additional challenges that we see is the advancement in the technology itself. Abilities of NICs and switches to grow to 10 gigs and 100 gigs and beyond. This increased the bandwidth, and in such modern networks, it pushed the limits of CPUs. So even very advanced CPUs can deliver packets at higher bandwidths, but at some points, they might not be able to do so. The radio network in 5G is using higher frequencies, meaning that there are much more locations, more cells, and this means that whenever we are moving in transitions with our mobile, it means that there are much more handoffs between the mobile cells, and this actually implies on the UPF, because if I am as a subscriber is served through a single UPF, this UPF now needs to handle all these kind of handovers. So it means that it needs to know where I'm located at each time. If we're talking about offloading, it means that if there are rules, the rules should be transitions from one IP to the other. So there needs to be some kind of ability to maintain the large number of insertion and deletion of rules. And there is expectations also to provide low energy and much more efficient network. It is required not just for a cost perspective, but also due to the fact that the UPF sometimes resides in locations in which the power is very limited. So we are looking for ways to reduce the power consumption. So I talked about the 5G requirements. Much of those influence on the UPF directly. And the UPF actually, as I showed in the picture beforehand, but it used as a router of IP data that serves the user plan for the user. It's from one end. So user data moves from the subscriber location through the RAN, and then there are two kinds of locations that the UPF can reside on. One of them is at the edge, and this is called the IUPF, intermediate UPF. It's a new kind of deployment in 5G that enables to put the routing much closer to the user. In some cases, it is relevant for factories, for example, or areas in which many users are using the same kind of data. So this allows the UPF to provide a direct access to the data network. Data network can be either the internet or a factory, machinery, servers, or whatever. And the other general purpose UPF resides on the core. Both of them are communicated through N3 network, which is the communication between the RAN and the UPF. And from the UPF, the data is going out to N6. What we see here on N3 is a GTP-based traffic. The GNB, G-Node B, the antenna, is taking the data and encapsulate it with a GTP header. This allows the mobility of the network. So the UPF itself, after decapsulating the GTP header, it sees the internal payload, and the payload contains the information of the subscribers. So wherever we are in the network, the payload remains the same in terms of IP of the subscriber. What might change is the outer header, which describes from which antenna you are coming and for which antenna we need to send the packets back. So this allows the mobility. The UPF itself on the uplink, and the uplink is from the user to the network. So the UPF on the uplink decapsulate the packet and then send plain IP to the N6. And the other way around, when packets get back from the network, the UPF encapsulates based on the information that it has about the subscriber. So it encapsulates it and sends it back to the antenna. So we see that the UPF needs to deal with routing in dynamic environments to allow delivery of the messages, packets between the different sites. What you do, it provides multiple functionalities as a router. It knows to filter the packets, identify the subscribers. Based on the information about the subscriber, it knows to apply different policies or provides rate limiting. As mentioned before, is a use case, for example, to rate limit download and to allow a high rates for voice. It also manages counters for charging and quota management, so that different telcos will be able, for example, to maintain services such as prepaid and knows specifically when the data is about to need to negotiate a new plan for the subscriber. From scale perspective, there is a requirements to maintain as much as possible in order to reduce the prices. So the higher the capacity that each server can maintain, the lower the cost for the telco. So today, in terms of expectations, we are looking about 10 to 110,000 modified connections per second for maintaining 100K of subscribers with millions of flows, high bandwidth for each of the subscriber, meaning high MPBS in total. And the expectation is due to the fact that it serves not just mobiles, but also remote machinery and other use cases that needs to be interacted interactively. For example, in safety and city IoT for cities, and in which you see videos that need to act upon. The expectation is to provide low end-to-end latency. Additional things that the UPF does is that it allows to manage aggregated counters and meters. Aggregated counters are relevant, for example, to establish means to identify all the video traffic of the subscriber or the social traffics. So there are some kind of telcos that provides plans for free social surfing and for a specific package. So in that package, if the subscriber is using Facebook or Instagram, the UPF is able to count only these kind of traffic, or actually don't count them, but count the others, and allow the telcos to maintain the counters to understand whether the subscribers can get through to the network based on his plan or not. So how does it work? So there are some initials here. The first is the PFCP. This is the protocol between the SMF and the UPF itself. The SMF provides insight for the UPF about the subscriber and what kind of detection rules UPF should use in order to identify the subscribers. This kind of detection rules provides further insights about the forwarding actions, whether to do not, whether to provide direct access to database or to a specific location, such as shown in the IUPF. It also provides insight about the quality of service and the usage report. The usage report is something that the UPF itself should be able to provide when he is asked about it. And this is something that the SMF and the charging systems are using in order to communicate with the UPF to assure that traffic that goes through it is aligned to the customer or the subscribers' profiles. Once the UPF gets the structure of the PTR, so in general, UPF without acceleration is managing this kind of structure in memory. When we discuss about offload, this kind of structure needs to be offloaded to the NIC, and we will just discuss about it in a few minutes. A few things to show here is that, sorry. Few things to show here is that there is on the left side we see the PDR. These are the packet detection rules. There are different kinds of PDRs. So there are PDRs for voice, PDRs for layer 7 filtering, to identify video, for example, and different other types that the telco can decide which of them to use. The ability to identify different kinds of PDRs allows later on to do the segmentation about whether the counter relates to this PDR or to this group of PDRs. This is one thing. The other thing is the uplink and downlink. For each kind PDR, there might be the uplink, the messages that are going from the UE, from the mobile to the network, and the downlink. And these are completely different. For example, in the uplink, there might be a need to do a DPI, in the uplink, in the downlink, not. We know specifically that on the uplink, you're doing the GTP decap. You don't do a decap on the downlink, but the opposite. You need to do the NCAP. It's a mistake here. And there are counters that you want also to maintain. There are counters that you want to maintain only for a specific session, just for the traffic that you're using, for example, for YouTube. But there are also shared counters. The same counter that you use for YouTube, you might want also to use it for a Disney video and for Netflix, and this to allow to count all the traffic that goes for video traffic. So this is the base idea about what PDRs are used for. Now I want to make a short distinction about what acceleration is. DPDK is all about acceleration. It starts with accelerations of the infrastructures. So what we see on the left is the acceleration of the infrastructure, where packets are going through a port, either physical port or virtual function, and then accelerated, in this case, through SRIOV. So the data is going from the NIC directly to the application in a fast way, and then the applications performs whatever it needs to do and sends the packets back to the network. This is regular accelerations. In these sessions, we are looking about different kinds of accelerations, which is actually applying all logic that generally applied on the software, on the CPU. In this case, it is applying this kind of rules of switching capabilities inside the NIC itself. DPDK is supported today through the RTE Flow API. It allows through RTE Flow to define the different rules, and applications defines them for the NIC, and for all those packets that fits the rules that were identified in this kind of offload, the NIC handles the packets instead of delivering them to the applications and then expecting the applications to do the work. So what we are seeing on the right side, we see that there are two virtual functions. The packets, the lower one. Sorry. We are seeing here packets that goes into a VF, and then there is an action called hairpin that moves the data from one VF to the other, then the packet goes. Of course, there are additional actions involved here, otherwise we are just delivering the same packet. So once the packet is here inside the NIC, there is an embedded switch that applies the rules, identify the packet, and can perform multiple actions, one of which will be to do the hairpin and then to go out to the network. Hairpin is supported today for moving data between different ports, but of course you can go out to the same port. And in terms of what you're doing next, there are multiple kind of actions that can be done. We also see in this picture also the ability to do forwarding, and those two capabilities of offload goes together. This allows to maintain the slow path that will go to the application. The application here apply DPI logic, understand what the packet is all about, whose subscriber it belongs to, and then offload the rule to the NIC. The first packets, and maybe several more that are required for the DPI, are then served through the UPF application through the regular non-offloaded mechanism, but afterwards, everything else can be handled in the NIC itself. So a little bit more about what the embedded switch is doing. The embedded switch is an ASIC-based classification and action engine. It knows to manage rules similar to what we know in OVS, for example, but not just on the switch level, but also on layer 3 and 4. It knows to manage tables and actions. For each table, there is a classification or match, it's the same, and several actions that can be done. These actions varies. They can be doing the encapsulation, decapsulation, counting, quota, and many others. And one of them is forwarding, and forwarding can be done to multiple locations. It can be done forwarding to another table that also identified in the pipeline, or it can be forwarding to another port or to the software. So by using this kind of classification engine mechanism, it is possible to define a complete pipeline, and the pipeline is built either on one classification and several actions, or one actions, or multiple classifications that are traversing from one to another. Specifically to the talk that we are doing today, the classification is based on a GTP header, including a header extension that is required in 5G, and the action are encapsulation, decapsulation of GTP, doing RSS that we will see in a minute, using hairping, counters. We are also using flow tags, which is the ability to define a specific metadata for the packet. We are using it to identify the user. There is a field in the GTP structure that is called TID. We are identifying it and applying a tag. Then the application can use it, and I will touch it again, so just remember it. There are other capabilities that we are still not using today, but are also important. For lawful interception, for example, you can do mirror of the packets. So some base assumption before we see how the UPF work. The assumption is that the UPF use DPDK and offload the packets detection rules through the DPDK. These rules, although they can appear in asynchronous manner from the SMF, the DPDK doesn't offload them immediately, but rather expect to see what actual sessions will come from the subscriber. So the way that it goes is that once subscriber's packets arrives in a fashion of just-in-time and inline the traffic itself, the data is accepted by the NIC. The NIC try to find the correct rules for it using the match mechanism. Once he sees that these rules are not listed in its memory, this is a misflow. So it goes to the software. The software applies DPI. Based on the DPI, the UPF knows which rules to apply, then do its offload, and everything else can be treated in the NIC itself. One more thing is that once all the traffic is handled in the NIC, the UPF lose touch with the notion of what happens with the subscriber. So if the subscriber is a prepaid subscriber, in generally it maintains counters and knows whether to provide service to this subscriber or not. Once the flow is fully offloaded, the UPF doesn't know anything about this user. So all the counters that the NIC counts, they can be fetched and queries by the UPF. So the UPF once in a while, once in a second, or can be even much more than once in a second, the UPF queries the counters, identify which are close to their limits, and based on that, perform other stuff. You can decide whether to change the rules for the subscriber or negotiate changes in the plan for the subscriber and other things. From the DPI point of view, it is part of the pipeline, but it is part of the pipeline of the application. So it is up to the UPF how the DPI works. From the NIC perspective, as long as nothing was offloaded, all the rules are going to the software. So this allows for the decisions whether you want to do offload or not. Some of the reasons not to offload is that if the packets describes short live sessions, so it might not be efficient to offload them, for example, DNS sessions or things like that. And just as a reference to the pipeline, this is a reference pipeline just for the discussion. Pipelines might look different. For each subscriber, pipelines look different, and even for the same subscriber, pipelines of video is not the same as a pipeline of data, and so on. So I will use this as a sample pipeline, and the way that it is shown here, it looks like everything goes one after another. So in terms of packet flow, they're actually going one after another, but in implementation-wise, it might be that we are using a multiple table in the memory in order to implement them. Okay. So UPF without acceleration is using regular CPU and regular NIC, sorry, and all the data go to a CPU, and then there is a dispatcher thread that is working here very hard, and so much hard that in some cases when the traffic goes beyond some limits, it might be that the CPU cannot handle it. Elephant flows, or I don't know. So what the UPF do is doing the dispatching, and then after dispatching, each core implements its own pipeline. First thing is doing the DPI based on the match, and so on. So the limitation that we have here is that we are limited by the single core performance, and we have a poor efficiency. So we are looking for ways to implement something better than that. One way is to use the RSS. RSS provides the ability to do some of the work here on the NIC and the rest on the server. So some of the work here might be the match, identify that this is a GTP-oriented traffic, based on that to do the decap, and then to extract the TID of the subscriber, send it to the cores, and then what the UPF needs to do, it can identify which subscriber it is based on the TID. It doesn't need to do GTP anymore because we have done it also already in the NIC. So the rest of the work here is the same except for two things. One of them is the GTP is eliminated. The other is that the match is much more relaxed. Instead of doing a 5-tuple match, you can do a match on the TID, which reduces a lot of CPU power here. And we also reduced the use of the core here. Actually 2 cores, one for the uplink and the other to the downlink. And we also removed the reliance on single core performance. Another thing to remember here is that the RSS itself needs to be with core affinity. Core affinity means that for the same subscriber, the same core will handle the traffic. It helps for 2 things. One of them is to maintain the order of the packets, and the other is to eliminate locks between the cores, so that each core will handle the traffic for the same subscriber, and every time that you see the subscriber, we have it in the thread local storage instead of going to fetch it somewhere and doing locks for that purpose. And then the holy grail is to do a hybrid, something that will allow to do a full offload. And full offload is the way to start with partial offload. And then once the UPF application understands which traffic it is all about, it offload everything to the NIC. So what we will see here is a hybrid solution in which first packets goes to the traffic, and then once they are identified by the DPI, the rest of the traffic for these sessions is running on the NIC in full offload using AirPin, which is crucial here, and RSS is also used beforehand for all the other packets. This solution provides good, and by looking at it first, we started with the implementation of DPDK, and most of the actions that I just described were implemented already, actually all of them. And what we found out is that it is very crucial to do this kind of insertion very fast. So these are the findings that we have seen following this integration. It is very important to do a fast offload, because in the UPF and the way that it works, the traffic of the data plane and the control planes are somewhat aligned. It is not real control plane. It is not the control that is coming from the SMF, but it is the slow path. And everything in the slow path, at least until the in this method is offloaded, it should be treated as it is a fast path. Otherwise, during the cycles that the CPU waits for the NIC to insert the rules, it could have been able to manage additional sessions and additional packets for additional subscriber. As long as it waits for the NIC to respond or to insert the rules, we are losing time and we are increasing the latency. So in order to maintain low latency and maintain the high rate and allow concurrency of multi-threading, the insertion should be very fast. One of the things that might help here is to make a better implementation. And the other thing is to think also what you are about to insert, what you are about to offload. Not to offload everything. I mentioned before, and TNS might not be required, but maybe there are other short life sessions. One other thing is the core affinity. Core affinity is a base requirements. Being able to do hairpin for full offload. Otherwise, we can offload much of the traffic, but if we go to the software, we're breaking the ability to do full offload. There is a great difference between running a packet only in the hardware and running a packet partially in the hardware and partially in the software. Even if we do all the pipeline in the hardware, if we have a single item that we need to do in the software, it breaks. It is a completely different set of latencies. We also identified that specifically for UPF, maybe for other applications as well, but specifically for UPF, there is a recurrent pattern, the same workflow and different instances. Many users will be applied with the same kind of workflows, but they will have different counters and different values for the counters, but the pattern is the same. And the pipeline structure influence on the performance means that in some cases you can do this section and the other afterwards, or you can switch the ways, or you can maybe align them together. So the definition of what kind of structure you choose for the pipeline influence on the performance itself, because the NIC itself needs to identify the rules, needs to go between tables, and if you're able to find a common work and do it first, just for those that are relevant, so you can reduce the time that it takes the packets to go inside the hardware itself. So what we did with these findings? So we extended RTF flow and introduced the template API. The template API allow for implementations of resource pre-allocations, so that instead of allocating memory every time that we offload a rule, we define templates of what we are about to do, and we are setting up the memory up front, so that the application in the initiation phase can define all the shared pipelines, which actually allows to reduce the memory and the time that it takes to insert a rule. It also defines the shared object. If we have counters that we are going to count for multiple sessions, so we can define them in the initiation phase, or at least the structure or what we are going to use them. And then we can pre-allocate everything. We identified which templates we are going to use. This would dictate the tables that we use, which kind of matches are aligned with these tables. And then when we say what is the size of the table, the NIC itself will allocate the memory. And then the memory management will be much more smoother during the runtime. And then come the runtime. In the runtime, the packets goes, and just in time, we will do the rule offloading. Rule offloading is the insertion of the rules, but also the deletions of those that aged out. So in the template API, we have changed the mode to work instead of async mode. We are doing instead of sync mode, sorry, we are working in async mode, in queue-based and lockless, so that the application offloads the rule and then can continue. It doesn't need to wait for, and there is also an API to query the results, and there is a way to do it efficiently. And rule offloading are done through the way that we are not building the pipelines every time from scratch. We are building just the instances that influence on existing pipelines that we defined in the initiation phase. All this can be done in asynchronous manner and also can be done in bulk. Everything that we are offloading, we can let the NIC know whether it is crucial to do it now or wait for the next command. And this allows to do it in bulk. Important to say, it's critical to build the correct pipeline. As said beforehand, it's related to the memory management and how the NICs works. So if you build the same pipeline on different ways, it might consume more memory and more time on switching of the rules in and out. So here's a list of high-level changes that we have made in DPDK, some of which were relevant for template API and some were present even beforehand, but still yet needed to be re-implemented. First and foremost important is the thing to do the iRules exchange, and then the ability to support the GTP on the different flavors, either on the ability to look on the extension header and also to do RSS based on the inner layer of the RSS, which is based on the subscriber source IP. To support symmetric RSS, support shared object, hairpin, and some more. So this is my last slide, so we can stop there. So, as said, I've described the summary of work that we have done together with Mavenir. We implemented and validated the commercial UPF. They've implemented it using DPDK, and we are still working on further offload there. We introduced RTFlow template API. It is already mature. We think that it can be used for UPF acceleration. We have used this code with multiple offerings that we have to validate it and to see what kind of performance we can get. The transitions from one NIC to the other didn't require any change in the code. And we encourage everyone that is building either UPF or other VNFs to use DPDK RTFlow and help us to be better with it. Yeah, that's it.
Hello. Thank you for the presentation. So my question is regarding this work you have done for improving the offload of the flows, of the rules. So you are using this kind of queuing, then specific API for knowing which is the state of this offloading. So how much of that problem of the offloading is related to DPDK RTFlow, and how much is a limitation of the hardware?
So actually we have implemented in software things that we already built in hardware. So the way that we build the way that enables us to do it asynchronous is by applying logic on top of what was implemented in the hardware. The hardware itself was capable to define pipelines in a way that you will send it through the traffic pipeline, a kind of command that says what kind of rules you want to build. Prior to that, we have done it differently. We have built the structure directly in memory, and that was on the expense of the CPU itself. Now we are building the structure and sending it through the network, and the NIC takes it together with the traffic. So it doesn't interfere with the traffic. It is handled in hardware much faster, and that's it.
So how much is the delay between the offload starting in the host until the hardware can use that flow? Have you?
It depends. You cannot state specific value. I can tells about the scale. The scale is millions per second. And the reason that I can't state something specific is that it depends on the traffic itself. Because it is not a single rule. When we define, as I said, as I described a pipeline may be built of multiple tables. And a pipeline might be built on a single table. So it depends how many rules you have in the pipelines, whether you have a single table or not. So this would dictate how many instances data you need to send and how much work the NIC will need to do in order to extract the information and build the pipeline actually.
Sorry to interrupt. I think that what you mean is what is the level issue with the software if the upload catches the word. This is
right, yeah.
So, sorry to interrupt. So basically, we don't have exact numbers to give you. It's, I would say, around microseconds or something like this. Until now, what happened is the RTE flow was synchronous and basically returned only then. Sorry.
Yeah, that's a good point. So it's synchronous, and now you are doing it asynchronous because synchronous is too heavy for the CPU. Because it needs to wait some signal from the hardware. Okay.
Exactly. So basically, it's asynchronous, and the idea is again.
Sorry. So sometimes you can have a big delay there.
Yes, but it's also probable that even if you do synchronous, well, if you look at UDP traffic, for example, okay, think about it like this. It's fast. Okay.
But just a minute. I think it was important questions about the sometimes delay. So I think that in the way that we deploy it here, and due to the fact that most of the structures are the same, so sometimes is if you are in the lab, but when you are applying UPF, so there is no kind of sometimes. You already knows what the pipelines are. You already defines what the structures that you are about to implement. And this will provide you a high level of accuracy and alignment of the time that it takes to offload this kind of rule and the others. So there will not be a differentiation between the different rules. So all in all, I think that if we compare it to the earlier software-based solution, in which you can have hiccups of the CPU for sometimes, so here it is eliminated.
Okay, for a specific question about RT flow, we'll have a working session this evening, so any question is welcome. Any other question about 5G? Yeah, one quick one.
I have a question regarding the fragmentation.
Fluctuation?
So, fragmentation, basically out of ordering scenarios. One is if you get a fragmented packet, how ordering is taken care. Second thing is, especially...
I did fragmentation, okay.
Yeah. So for UDP traffic, like before the rule gets inserted for offload scenarios, before the flow gets offloaded, there will be out of ordering. There will be a transient period where there will be out of ordering before the first packet that is sent is getting re-injected, right? How those scenarios are taken care of.
So let's start with the first. In regards to fragmented packets, in order to resolve fragmented packets, you need some kind of buffering in the NIC, and this is something that we currently don't have.
Okay.
Or those that we have, we prefer to use them for the data plan. So what we suggest in terms of fragmented packets is just to have a rule specifically that identify fragmentations, and this is also kind of a match that we have added. So fragmented packets will go to the software. The software can rebuild the packet, and then the software can inject it back to the NIC to treat it as a whole packet without the notions of the MTU size and things like that. So okay. This is for the first questions, and can you repeat the second one?
Second question is for offloading scenarios, right? Like, if your flow gets offloaded, the first packet goes through the CPU, the flow gets injected or added into the accelerator, and the first packet gets re-injected, right?
The first packet is going to the software, then the DPI. The offload of the rules is not getting immediately. As said, it depends on the DPI. And with our experience, in most cases, it doesn't happen on the first packet. So it takes few packets until the DPI knows to do that.
Okay.
As long as the DPI is not offloading the rule, there is no rule in the NIC, and all the packets that belong to the same subscriber will continue to go up to the software. So only after the DPI do the offload, only then the traffic will go only in the NIC. And due to the fact that we are doing it asynchronously, there is a need to maintain some kind of status or a state machine that states whether this traffic is already in transition to be offloaded or whether it was already offloaded. This is important to identify whether the UPF read the counters from its memory or from the NIC itself.
Okay.
Quick question. Is it software forward? The first packets, are they software forwarded or held back and then rejected?
The first bucket is handled completely by the UPF, and the UPF also implements all the pipeline.
Okay.
So as long as it doesn't know what traffic it belongs to and how to treat it, and what quality of service and so on, it treats it in full. And only when the DPI decides to do the offload, he's doing the offload. But again, he's doing it only after he's dealing with the traffic itself.
I see there is a lot of questions, but we need to.
By the way, everyone,
you're
welcome to.
Yeah. So we will have a break.
Everybody
is welcome to ask questions to Gal about 5G. That's more than welcome. And talking about that, we plan to have a webinar dedicated to 5G, probably at the end of this year. But in order to make it very interesting for everybody, there is a call for action, call for content proposal. If you are an expert or you know an expert in this area, please propose. We are going to build this webinar soon. And by the way, if you have something to propose, please discuss with Gal or with Elena, etc. With Tobias, probably they have something to say about it. Okay, thank you everybody, and see you very soon for the rest of the talks.